Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and it's time to go through question number 7 from the 2018 AP Chemistry exam. Before we get started, I want to remind you that this is one of the short free response questions. It's scored out of 4 points, and sometimes these short questions are kind of hard to earn the points on. You'll need your calculator, your periodic table, and your formula sheet. I do strongly recommend, as I do every time, that you try to work through the entire problem on your own before you listen to my answer key and listen to me talk through the solution. That's really going to be the most effective strategy here. And then keep track of your score as you go. Did you get the point or didn't you? All right, what do you have to do to get each point? It can be kind of tricky sometimes. So let's jump right into the problem. It starts with a photoelectron spectrum. All right, it says it's the complete photoelectron spectrum of an element, so all of the electrons are present, and you're asked to identify the element. Now, this was scored out of 1 point. All right, and the answer is nitrogen. How do you get there? How do you figure out that it's nitrogen and not some other element? All right, well, we do know all the electrons are included, and that's actually important. All right, so when you're interpreting photoelectron spectra, what you have to remember is that electrons that are in sublevels close to the nucleus experience a stronger Coulombic attraction to the nucleus, and therefore it's going to take more energy to remove those electrons. Now, electrons farther from the nucleus in sublevels that are and higher principal energy levels and farther from the nucleus will have a lesser attraction to the nucleus and will take less energy to remove them. All right, and therefore that peak that's just shy of 40, that's going to be our 1s sublevel, right? Well, that's the closest to the nucleus you can get. All right, and the next peak at about, it looks like it's about 2.5 would be our 2s sublevel, and the third peak is the 2p sublevel. All right, so what we know is we're looking at a P block element in energy level in period 2, because the energy level 2 is the highest occupied energy level. Great. All right, how do we know it's not nitrogen and not oxygen or carbon or one of these other guys? Well, that's where we have to look at the amplitudes. All right, the 1s sublevel should be completely filled here. The 2s sublevel should be completely filled if we're looking at a P block element, right? And I see that the 1s and 2s peaks have the same amplitude. So I'm going to take that to mean they each have 2 electrons, because that's how many electrons would completely fill that sublevel. So when I look at the 2p sublevel, I notice that the amplitude of that peak is a little bit higher, but not twice as high. And so I'm going to interpret that to mean it's got 3 electrons in it. That's why it's nitrogen, right? Because I have 2 electrons in the 1s sublevel, 2 electrons in the 2s sublevel, and 3 in the 2p sublevel, right? And so that's how I know that it was nitrogen. All right, and so that peak amplitude is really important, and that's how I knew I had 7 electrons and not 6 or 5 or 8 or anything like that. All right, and so I know it's a fairly easy question if you know how to read PES spectra, but I know when I gave this question in class to my students, most people, but not all my students, got it correct. Right? It's not hard to make mistakes with interpreting this. All right, a radioactive isotope of the element decays with a half-life of 10 minutes. Okay, so there's a radioactive isotope. Half-life means half of the radioactive material will react or decay in 10 minutes. Calculate the value of the rate constant for the radioactive decay. Include units with your answer. Now, this question was scored out of 2 points. And if the half-life is constant, that's telling us that it's first-order kinetics. That's really important here, knowing that it's first-order kinetics, because that's really where half-life is the most useful, all right? So first-order decay, a constant half-life, that's an important thing to know about first-order decay. And there's an equation on your formula sheet that the half-life is equal to 0.693 over K, the rate constant. So we can easily rearrange this, right? And at this point, all we have to do is substitute and evaluate. So the key is really knowing that, it's going to be first order decay, because all radioactive decay is first order. And I can take this equation and rearrange it. So now I'm going to substitute in my half-life and get a number of 0.0693 inverse minutes. All right. One of the points for this question was getting the correct numerical answer. And the other point was just for the units. Now, you were prompted in the question to include your units, all right? But it needed to be 1 over minutes, or minutes to the -1, inverse minutes, because that's the appropriate unit here. I suppose if you had converted your minutes to seconds, you would have a slightly different numerical answer. Don't make extra work for yourself. This is absolutely sufficient in terms of the work. All right, and then there's one more part to this question. If 64 atoms of the radioactive isotope are originally present in a sample, how much time will pass until you only have one atom of that radioactive isotope? Show how you arrived at your answer. So you are expected to show some math work to support your answer. All right, it was scored out of 1 point. And if you know how radioactive decay works, it's actually pretty easy. So the moment the time starts, at time 0, we had 64 atoms. And we're going to just keep dividing by 2 and figure out how many half-lives elapsed. So I'm not going to go through each one individually. I'll just show them all at once. All right. After 1 half-life, after 2 half-lives, I just keep dividing by 2 until I get to only 1 atom remaining. It took 6 half-lives for that to elapse. So if each half-life takes 10 minutes, then 60 minutes must have passed. I mean, that's probably the easiest way to do it. And this method works really well as long as you have integral numbers of half-lives, which you don't always have. It does tend to be the case in this problem, of course. But sometimes if you don't have integral numbers of half-lives, you might want to use the first-order integrated rate law, since we know that this is first-order kinetics, right? And so if you look on your formula sheet, you've got an equation, ln of AT minus ln of A naught equals negative KT. Now, to do this approach, you do need to use your rate constant from the part B, all right? But we're not required to have integral numbers of half-lives. If it had been, 3.72 half-lives, this would be the way to go. And AP Chemistry students do need to be able to use this approach. It's certainly fair game to ask you to use this problem. So all we have to do is substitute in. All right, so the concentration at time t would be 1, all right? Whereas the concentration at time 0 would be 64. We can just put in the numbers of atoms, all right? So I can take the natural log of 1 minus the natural log of 64 equals negative 0.0693 times t. I'm solving for t. All right. Well, hopefully you know that the natural log of 1 is 0. All right. But you can play it, just get that from your calculator. Take the natural log of 64 equals negative 0.0693 t. Solve for t. And again, you get 60 minutes, which is reassuring that you got the same answer. So either approach is fine. You do need to show your work either way. All right, so the question is, how did you do? All right, the average score on this question when it was the exam in 2018 was 2.02 points out of 4. So I think they were pretty strict about the scoring. All right, units for the rate constant, correctly identifying the element, interpreting the PES data, correctly doing the math for the half-life determination calculation. Students sometimes forget to start at time 0. So there are definitely ways to make sure you get all the points, but there's definitely places where you can easily make errors. And I just want to remind you, if you haven't already, subscribe to my channel. Have a great day.